So today's notes, section 14.5, which is the chain rule. So we're going to review the chain rule that you all already know and then talk about how it applies to Calc 3. In Calc 1, sometimes you were given y as a function of x, and then maybe you were also given x as a function of some variable, like maybe t. And then you wanted dy dt. So this is not how you guys think of the chain rule, but this is how it's going to look for us. For something like y of x of t. So if you wanted dy dt, you first had to differentiate y with respect to x, then you had to differentiate x with respect to t. Does this look vaguely familiar? Mm-hmm. So it's not generally how you think of the chain rule, but it does come up like that. So now what we're doing, we're going to have a function of two variables, sometimes more, but maybe we have z that is a function of x and y. And you're going to have x is some function of t, and y is some function of t. So then we can write z as a function of just t, a single variable. So it's f of x of t and then y of t. So that expresses z as a function of a single variable. Which is t. Here's the chain rule for this specific scenario. If I am looking for dz dt, I'm going to take the first partial of z with respect to x, then dx dt. To that, I'm going to add the first partial of z with respect to y times dy dt. Okay, so a few things we need to notice here is we have partials and then we have regular derivatives. So these two are both partial derivatives, and that's because z is a function of more than one variable. That dy dt and dx dt, these are not partials, and that's because x and y are just defined in terms of t. There's only one variable, so you don't take a partial derivative in this case. Okay, so here's our first example. Let's say z is the function x squared y subtract y squared. X is equal to sine of t, and y is equal to e to the t. We are going to find dz dt at t equals 0. Okay, so our first option, if we didn't want to use the chain rule, would be to plug in sine of t for x and plug in e to the t for y. That works. It's not generally going to be the most efficient way, so that's not the way we're going to do it. We're going to do it using this chain rule that's above. So we get dz dt. We need to take the partial of z with respect to x. So that'll be 2xy. And then we have dx dt, so differentiating with respect to t, and you get cosine of t. Then we are differentiating z with respect to y, so we get x squared minus 2y, and then dy dt, which is e to the t. Now, we want everything in terms of t. So once you get to this spot, you're gonna have to substitute in x and y. Okay, so our x is sine of t, so we get 2 sine of t, cosine of t, and then y is e to the t. X squared is sine squared of t, subtract 2y, so 2e to the t, and then we have e to the t. So ultimately, we were asked to evaluate dz dt at t equals 0. If we do that, sine of 0 is 0, so all that is 0. That's 0, that's 2. We get an answer of -2. Okay, so real quick, I also want to do the same problem if we didn't use the chain rule. So if you didn't want to use the chain rule, you need to write z as a function of t. So you're going to substitute in these two functions for x and y. So we get z equals sine squared t times e to the t minus e to the 2t. And then you would just differentiate this like normal. Derivative of sine squared is 2 sine of t cosine of t, e to the t, and then plus e to the t sine squared of t minus 2e to the 2t, which is exactly the same as what we got using the chain rule. So I would say in this case it's a little bit easier to not use the chain rule, but you still need to know this idea because there's going to be other problems where it is significantly easier to use the chain rule. Okay, questions so far? Okay. So the chain rule is going to extend to any number of variables. So for example, let's say that we have w, which is a function of x1 of t, x2 of t, etc. If we wanted dw dt, we would take the first partial of w with respect to x1, and then the derivative of x1 with respect to t. And we would keep going. First partial of w with respect to x2, and then differentiate x2 with respect to t, and so on. Okay, things are going to get more complicated though. Oftentimes x, y, whatever variables you're using are not just going to be a function of t, they're going to be a function of multiple variables. So you might have z as a function of x and y, but then x and y are a function of u and v. So there's a lot of variables that are involved. When things get complicated, we're going to use tree diagrams. Okay, so here's how the tree diagram works. Let's just use the case we've already looked at, where z is a function of x and y are a function of t. Okay, so here's how your tree is going to work. You start with z. Z is defined by x and y. X is defined by t, y is defined by t. So then what you want to write along those branches is the derivatives that you're going to take. So because z is defined by two variables, these are partial derivatives. X is only defined by 1, so this is the derivative dx dt, and then dy dt. If you are looking to take the derivative of z with respect to t, you're going to go to the bottom of the tree and find all the t's. So here's an example. Z is a function of x and y. X is a function of u and v. Y is a function of u and v. We are just going to write the chain rule for partial z, partial u, and partial z, partial v. So here's how this is going to start. Z is defined by x and y. X then is defined by u and v. Y is defined by u and v. In this case, every variable, or the z is defined by two variables. X and y are both defined by two variables. So any derivative you take is going to be a partial. So now we're going to fill in the derivatives along the tree. So this will be partial z with respect to x, partial z with respect to y. Here now, this will be partial x with respect to u, partial x with respect to v, and then partial y with respect to u, partial y with respect to v. So if I'm looking for partial z with respect to u, I'm looking for everything that ends in a u. So that would be here and here. So I need to follow the branch to get to that point. This one right here will be partial z, partial x, multiplied by partial x, partial u. And then I have to go this way. So it'll be partial z, partial y, times partial y, partial u. Same idea when you're doing the partial of z with respect to v. So you're going to have to get down to this v and then get down to this v. So it'll be partial z with respect to x, and then this time partial x with respect to v. And then we have partial z with respect to y times partial y with respect to v. Okay. Do we get the idea of the tree? We do? Okay. We're going to do a few examples. Here's the example that you're going to do. Well, we're going to do this one together. You guys will do the following one. Let's say z is the function 2xy. X is the function u squared plus v squared. Y is the function u over v. And I want us to find partial z with respect to u. Okay, so first thing I want us to notice is this is exactly the scenario that we carried out in example 2. Z is a function of x and y are functions of u and v. So we don't really need to draw the tree and do the chain rule again because we already figured it out. So we're going to do this one right here. So partial z, partial u then. It'll be the derivative of z with respect to x, so that'll be 2y. And then the derivative of x with respect to u, so that'll be 2u. Partial of z with respect to y, so that'll be 2x. And then the derivative of y with respect to u, which is 1 over v. Y and x we cannot have in there, so we're going to have to substitute those. Is it okay if v is there? Yeah, because if you take a partial with respect to x, isn't y there sometimes? Yeah, so the v is okay. It's the y and the x that are not okay. Okay, so here we get 2. Y is u over v. That's 2u plus 2. X is u squared plus v squared. That's 1 over v. Okay. If we're simplifying stuff, this is going to be a 4u squared over v plus 2u squared plus 2v squared. So then final simplifying, we get partial z with respect to u, 6u squared plus 2v squared all over v. Okay. questions before we do one more example? Okay. So you are going to find dw dx for w is xy plus yz, and then y is sine of x, and z is e to the x. So I'm going to give you a few minutes, but here are the things I want you to do. I want you to draw a tree diagram. I want you to write the general form of the chain rule for this example, and then I want you to substitute in the specific equations we have. Does that make sense? Okay, take a few minutes to do that, please. You are welcome to talk to anyone next to you if you would like to. When you have a chain rule, I would like you to check with someone next to you. Because if you have the wrong chain rule, everything else is going to go downhill. Okay, we're going to take one more minute. If you have not checked with someone next to you, please do that. Okay, here is the tree that I got. Did you guys get the same one? So w is defined by x, y, and z. Y and z are further defined by x. So there's 3 paths you have to consider. The first path, the second one, and the third one. This is the general chain rule for dw dx. Please make sure you have the right partials and the right just ordinary derivatives. And then that was what I got as a final answer. How did we do?
Good.
Not well.
Get it now.
Okay, good. Questions on the chain rule before we move on?
Is that y to the z power in the equation?
What equation?
For w equals xy plus y to the is it y to the z power? Oh no, it's y times z.
Okay,
Never mind. That screwed me up.
sorry.
That's okay.
Okay, our next topic. One of our favorites that you all think you're good at, and maybe we're not amazing. Implicit differentiation. Yes. Okay, let's consider the following equation. Y cubed, add y squared, subtract 5y, subtract x squared plus 4. This you've done before. So the goal, in this case, was to find dy dx. Okay, there is 2 different ways to approach this problem. One is the Calc 1 way and one is the Calc 3 way. We're going to do both. So here's what you did before when you guys were in Calc 1. You took the derivative of each piece. So the derivative of y cubed, you got 3y squared, but then dy dx plus 2y dy dx minus 5 dy dx minus 2x, and that gets dx dx, but that's just 1, so you don't need to write anything. Derivative of 4 is 0, so we got all that equal to 0. You factored out the dy dx, you isolated it, and you got 2x divided by 3y squared plus 2y minus 5. That all look familiar? Okay. Here's how we're going to do it now. We're going to take that same equation, so that y cubed plus y squared, all that one. Okay, everything that's on the left side, we're going to consider that f of xy. So we're going to consider that a function of 2 variables. And then we're going to say that f of xy is equal to some value of c. So in this case, c is 0. Okay, f then is defined by 2 variables, x and y. X, we're going to call the independent variable. Y then, we're going to say is dependent on x. And that's the case because all this is set equal to 0. So they can't both be independent. Okay, so then what we're going to do is we're going to treat y as a function of x, just like you did in Calc 1. So if then we want to do the chain rule here, we would take the partial of f with respect to x, and then we would take the partial with respect to y times dy dx. Bless you. And we know that that has to be equal to 0. So if we isolate then dy dx, we get negative partial of f with respect to x over the partial of f with respect to y. All right, so I just moved this over and divided by the partial with respect to y. Okay, so if we look up here, partial with respect to x is negative 2x, but we need to switch the sign, so that's a positive 2x. And then partial with respect to y of this function is 3y squared plus 2y minus 5. So we end up getting the same answer that you would have gotten had you done this problem last year. Okay, I'm not going to have you do the same problems you did last year, though. Things are going to get a little more complicated. So we have one more problem to do, and then we are done with notes. So the last question we need to ask ourselves is what happens if we have more than 2 variables? So we're going to look at the case where we have 3 different variables. We have x squared add y squared add z squared equals 1, so the unit sphere. We are going to find partial of z with respect to x and partial of z with respect to y. Okay, so doing what we wrote before, we are going to call f function of x, y, z, and that's going to be everything on the left side. And we are looking at the specific case where f of x, y, z is equal to some value c. In this case, c is 1. Okay, so now we have to write our tree diagram. F is defined by x, y, and z. Okay, here's a little bit of the tricky part. How many independent variables do we have? 2. So before we said y is dependent on x. Now z is dependent on both x and y. Right? If we have x squared plus y squared plus z squared equals 1, you could manipulate any 2 variables. And then the third one is going to be dependent on the value of the first 2. So in this case, we're choosing to manipulate x and y to call those independent. So then we have 2 derivatives. The first one to get to x and then to get to y. If we go to x, we would take the first partial of f with respect to x. Other way to get to x would be to take the partial of f with respect to z. And then the partial of z with respect to x. And if we take the derivative on the right side, we're going to get 0. So then we see that the partial of z with respect to x, so what we were looking for, is the opposite of the partial of f with respect to x divided by the partial of f with respect to z. That was one option. We could have chosen y also. We're not going to do that because it's exactly the same process. But you end up getting the partial of z with respect to y is the opposite of the partial of f with respect to y divided by the partial of f with respect to z. You do not have to derive these each time. So if you have a scenario like this, you can jump right to those 2 formulas because they're going to be the same each time. So in this case, we get the partial of z with respect to x. If I take the first partial of f with respect to x right here, I'm going to get negative 2x divided by 2z, so it gives me negative x over z. Partial of z with respect to y, I'm going to get negative 2y over 2z, so negative y over z. Okay. You also can do this implicitly and get the same answers. We're going to do it real quick just to review it. Is that okay? Is that okay?
Yep.
Thanks for answering. Let's say that we want partial of z with respect to y. That means then we're differentiating.
I have a question. Where did this? When do you use the c equals 1?
When you take the derivative on this side. So really, you don't use it.
You don't.
It doesn't come up in anything, no. Okay, we good?
Yep.
Okay, so if we want to take the partial with respect to y, we will be taking the derivative of everything with respect to y. So we will be taking the derivative of y with respect to y, which is going to be 1. We'll be taking the derivative of x with respect to y. Those are independent, so that's just going to be 0. Okay, so then we have that x squared plus y squared plus z squared equals 1. Taking the derivative of everything with respect to y, so we get 2x, the partial of x with respect to y, plus 2y, the partial of y with respect to y, plus 2z, the partial of z with respect to y. That side it'll be 0. We already said this one was 0 because x and y are independent. So we get 2y plus 2z, partial z, partial y equals 0. So we see that partial z, partial y ends up being negative y over z, which is exactly what we got at the top. So if you prefer to do it implicitly, you're going to get the same answer. But what you can do is you can just memorize those two formulas instead, since we derived them, and it's a little more efficient. Chain rule questions.